Hey, BIGA explorers, welcome back to the BIGA Solutions channel that brings you the best of biomimicry, indigenous genius, and ethical artificial intelligence. Today, we're diving into the fascinating world of complexity, where simplicity is the ultimate sophistication. I will demonstrate that the physics and mathematics principles I used to play indigenous games at the age of 5 before first grade are taught at university in conventional science. I will then reflect on how all this comes together in BIGA Solutions. In case you don't know, BIGA is an acronym, BIGA, where B refers to biomimicry or innovation inspired by nature. I and G refer to indigenous genius, commonly referred to as indigenous knowledge. And then the A at the end refers to ethical artificial intelligence. You can learn more about the channel using the links to the launch video and previous episodes in the description below. Don't forget to hit that subscribe button and join the BIGA Solutions family. Back up and let's get the show on the road. Previously indicated, I'm going to use an example that's going to show you how complex principles can actually be applied in a very simplistic, fun way. I'm not great at drawing, but I've got a picture that I'm hoping will be able to illustrate my points. I also brought some props. Got a potato here. I also have a knife, which represents a spear. Since I don't have a spear, actually a spear, you hold it like that. So don't worry, I'm not going to do anything dangerous. The example that I'll be using today is from an indigenous game that I used to play at the age of 5, before I even went to first grade at school. All right, so I'm going to pull up this picture, which is an illustration, really. I'm holding here potato, which represents that round thing you see there. We didn't actually use a potato. Our moms would have given us a hiding for playing with food. But there was a natural tuber or a bulb, which is a plant like a potato. We would dig it up and get the tuber, which was actually edible. If you were out there looking after cows, goats, or whatever, and you got thirsty and there was no well nearby, you would actually dig this up. And in fact, the Khoisan, who to this day, some of them still live in nature, eat it and they get water because it stores the water. All right, back to our story. Where this game would play maybe 3, 4, whatever number, and would draw a line on the soil or in the sand, and would all stand behind this line. We wanted all of us to be at the same distance from the target that we would have to hit. So each one of us would then hold a spear. And since I don't have a spear here, I'll use this knife for illustration purposes. And the idea was then you stand behind this line, and about 3 meters in front of this line, you would have someone throw this tuber, which was more circular than this. Think of a wheel of a car, but it would be like a potato. So somebody would stand maybe 5 meters from us and throw this parallel to this straight line that would have drawn on sand. So the challenge you faced as a player was to then know when to throw your spear so that this rotating tuber, as it comes at high speed, it collides with your spear. And if you succeed in hitting it, which was quite a feat, by the way, it required a lot of skill, then you are the winner. Maybe that day the other boys do all your tasks that you're supposed to perform because you're the winner. Let's come back to this diagram which I put up, in case you've been looking at it and wondering what it means. So that one up there is called the tuber thrower. It's the one who is going to roll this tuber at high speed, as fast as he can or she can. We would play with girls sometimes. The spear thrower needed to consider the shape of the tuber, because you were allowed to look at it before someone threw it. So you get to be familiarized with it. Sometimes we would just say play blind, which meant that you wouldn't see the tuber before the game starts. You would just have to quickly make up your decision based on the rolling motion that it would be making. So the spear thrower had to consider, therefore, the tuber in terms of its shape and then the angular velocity, in other words, the speed at which it would be rolling down. And then the slope of the ground, you would need to understand, is it going uphill, is it flat, or is it going downhill? As this would affect the rate at which the tuber is accelerating if it is going downwards, or decelerating if it is going up. And of course, you needed to understand the distance from the tuber thrower to where you are standing, so that you can estimate where you want the collision to happen. You needed to understand the force of gravity that is pulling down the spear. Once you release it, so you needed to give it such a push that it will hit the target even after compensating for the pull of gravity downwards, so that the collision happens where you want it to happen. If you put too much, the spear will hit the ground before the tuber arrives. And if you don't put enough, the tuber will go past before you can stab it. It's not only the force, you needed to understand the angle at which you are releasing. Now, all these terminologies I'm using here, I didn't know them. All I know is I was an expert at stabbing the tuber. It was only when I was at high school and university doing mathematics and physics. In fact, in maths, we called it applied mechanics. We learned about projectiles. So projectiles refers to those things that can be lobbed or thrown, or even a bullet is a projectile. As soon as the thrower, the tuber, had released it, your small 5-year-old brain would have to instantly calculate the speed at which it has been released and instantly calculate where it will be to collide with your spear. What force do you release? At what angle do you release? You knew instinctively the angle at which to point, and then you would throw, and it would go and land and hit. But in science, I later learned the difference between speed and velocity. You can say your car is moving at 90 miles an hour or 120 kilometers per hour, whatever, that's the speed. But if you attach a direction to where displacement is happening, then it's called velocity. When this tuber starts to rotate, going forward in a particular direction, that speed of rotation, that's the angular velocity. You can measure it, for instance, in revolutions per minute. And that you can't know. You have no instrument to measure the thing. You have to use your own intuition to be able to know this is the speed by observation and split decision-making to then release your spear, take care of gravity, take care of the angle, take care of the force, and take care of the acceleration or deceleration of the target, and boom, you are the winner. Let's now bring it all together. How can you then use this to solve modern day challenges? You would have noticed that with this indigenous game, the way the brain operates, it does not split the various principles and say, now I'm dealing with angular velocity, now I'm dealing with gravity, now I'm dealing with the force of releasing the spear, now I'm dealing with the angle of tilt of the spear. No, all those computations are done in a holistic way. And that's how most of our indigenous genius solutions operate. However, to be able to use artificial intelligence, we have to use the proxy parameters. So we might have to have, in our case, maybe sensors, cameras that pick up all these things and enhance human decision. Let's say, for instance, we live in a coastal area and there is a storm surge and it's beginning to flood the houses or whatever, and you want to automatically open up your sea defenses. This kind of intelligence can be applied, where you have a number of considerations to be done at an instant, so that as soon as the water hits a particular level, the artificial intelligence triggers the lifting of these water defense barriers. But as it does that, it alerts the civil protection service providers, your police, or firefighters, ambulances, your paramedics. Everybody gets mobilized. Some people may need to be evacuated. So all these things kicking, and the biomimicry is beginning to give you that segue to say, let's understand how this complex solution is solved in nature, and then let's create artificial intelligence that's going to help us to mimic the way the indigenous genius has found a solution to this. I was watching a talk by one Dr. Leroy, who is specializing in indigenous science. He says science is the pursuit of knowledge, whereas technology is actually the application of knowledge. Quite often people confuse science and technology. Technology is not science. Science is understanding the concepts, like what we've been talking about now. That's science. It doesn't matter whether it comes from textbooks, comes from indigenous genius. It's science, because it's the knowledge. But when you take this now and apply it to solve actual problems, then you're onto something. You can design and develop a technology that can actually work. I have to sign off now. Always remember to go bigger, go bigger, go bigger.